Okay, so welcome everybody to the last morning session. Our speaker is Agnieszka Hejna. She is an assistant professor at the University of Wrocław. She got her PhD only 2 years ago, and yet she has already 10 publications. Agnieszka does research in harmonic analysis, in particular in Dunkel operators. Together with her advisor, Jacek Dziubański, she got groundbreaking results in Dunkel operators, and her contribution was essential. At some point, Jacek Dziubański told me that some of theorems of Agnieszka may destroy, or in fact, probably destroyed already a few possible PhD theses of people working in Dunkel operators. Well, you should know that there is quite a community of such people, and well, people were working, and then Agnieszka came, and that's it. Yes, and Agnieszka received a number of rewards for her work. The most prestigious is the Kuratowski Prize for 2023, which is awarded to young researchers below 30 years old for outstanding results. And before, she got also the prize of Polish Mathematical Society for young researchers. And right now she is on leave from Rutgers. After her PhD, she obtained a postdoc position in Rutgers, position for 3 years, which is called Hill Assistant Professor. Okay, please, Agnieszka, the floor is yours.
Okay, so thank you for the opportunity to give a talk today. And the topic of my talk is a gentle introduction to Hardy spaces. And maybe you have seen this term Hardy spaces before. And my main goal for today will be to explain what they are in, I think, a quite simple way, starting from the things which are known from the other lectures, not necessary harmonic analysis. Okay, and here is the plan of my talk. And I'm going to begin with something which is probably well known, Fourier series, just the basics. And then I am going to tell you what are approximations of identity. And then I am going to, starting from this approximation of identity thing, explain what are the Hardy spaces. And it turns out that Hardy spaces have many equivalent characterizations or definitions. So I am going to explain them, or even it's better to say that I'm going to state them. Okay, and then maybe if time permits, I am going to tell you something about generalization of this topic. And of course, these things which are included in my talks are something which is classical, and the essential part of this talk is based on the textbook, which you can see here. So let us start with the Fourier series. So Fourier series, so suppose that we have function f, which is continuous periodic with period 2 pi, classical thing, and then we know the Fourier series of this function. So if we have function, we have the associated series, which is over the sum of all integers of trigonometric function e to the power I and nx, with coefficient where the coefficient is given by the formula 1 over 2 pi integral from minus pi to pi function f integrated with trigonometric function e to the power minus I and y. Okay, so we have such a series, and very natural question is the series convergent? And if it is the case, in which sense? For pointwise or uniform sense, or in some norm? And then if it is the case that somehow the series is convergent, is this function f the limit of this series? That means that one can write down that the function f at the point x is equal to the sum given by this series, okay, which somehow means that the function can be written down as an infinite sum of trigonometric functions. Okay. And what is the natural approach to this topic? So the natural approach, if you have the series, will be to study partial sum. This is the definition. So here we can define the partial sum of the Fourier series. So we are taking the Fourier series, and we take Sn to be the sum of the terms with indices which are smaller up to the absolute value than capital N. And then if one writes down just the definition of Cn here, it is nothing but writing down the same in the other way. We see that this is something like that. Okay, and then we can somehow rearrange the terms in such a way that here you have the trigonometric function, so we can put this term here, very easy. Okay, and then you see that it is just the finite sum, so we can change the order of sum and the integral, nothing hard. And we can do so in order to write down this in very suggestive way to understand it better. So if one introduces Dirichlet kernel Dn to be the sum of such a trigonometric function, so this is called Dirichlet kernel. And if we define the convolution operation, which is the operation which takes two functions f and g, and it returns another function, and this another function is denoted like that, and at the point x it is equal to such an integral. That means integral from minus pi to pi of f y integrated with g x minus y dy. Okay, and then if we put the sum inside, one can see that the partial sum of the Fourier series can be expressed as 1/2 pi f convolved with this Dirichlet kernel. So this is just another way to write down the partial sum. Okay, and now, of course, we can ask about convergence. And it turns out that this question is not so easy. And of course, we have some positive results. So for instance, if one assumes that, let's say that the function f is C2, then it turns out that our SNs, our partial sum, converge to the function f uniform. So this is easy. But on the other hand, one can prove that I think it is just a calculation that the integral of absolute value of Dirichlet kernel, so Dirichlet kernel, it was the sum, it behaves as logarithm of capital N. One can prove this. And why it is interesting? It is interesting because using this fact, one can prove the negative result. And the negative result is that there is a continuous function f such that the partial sums at the point x, the Fourier set of the Fourier series diverges. So the question is not so easy. And the proof of this fact is an exercise for you. If you know functional analysis, it is nothing but its application of Banach-Steinhaus theorem. Okay, but it turns out that if you want to somehow approximate the function by trigonometric polynomial, there is another way to do so. And this another way is to introduce the Fejér kernel, which is another type of the convolution kernel, which is nothing but this arithmetic mean of the Richard kernel. That means from 0 to n minus 1. And it turns out that Fejér and Richard kernel give us somehow a way to approximate the function by trigonometric polynomial. And we have theorem. And the theorem is that this Fejér kernel is nice in the way that we have the nice convergence result. So if one assumes that we have bounded integrable function on minus pi, which is continuous at the point t0, then it turns out that we have the convergence result. That means that 1 over 2 pi f convolved with fn at the point t0 converges to the value of f at the point t0. Okay, and this is something which is usually the theorem which is proved on Fourier series course. And for the proof, I'm not going to give you the proof here, but for this talk, I'm going to treat this as a special case of something which is much more general. We will see. Okay, so in order to explain this, I am going to work in the continuous setting. Okay. I think that something is wrong. Okay. Okay. So now the continuous setting, the next part of our talk, and we will work on Rn, and let us define some special function with phi. Okay, and this function will give us a way to build up this approximation result. That means the way to approximate something. We will see the details. Okay, so
do you want phi to be non-negative?
Here phi, not necessary.
Not necessary. Okay.
Okay. Okay. So we have the continuous integrable function in that sense. I have to write them down here, and we assume that this phi has integral 1. Okay. So something like nice function, and then we define the scaling of this function. This type of the scaling is called sometimes L1 scaling. Okay, so we define phi t at the point x to be the function phi state in that way. That means that if we have the function phi here, then we consider the scaling of this, which can be treated as the scaling of the shrinking of the graph of the function. That we look, for instance, like that. Okay. And now some examples of the function phi, which we can consider. So, for instance, one can consider phi to be Gauss-Weierstrass kernel, which is a well-known function, which is some constant c e to the power minus x squared. This t is taken in such a way to guarantee that the integral of this function is 1. So it's just the scaling factor. One can consider the Poisson kernel of this function like that, 1 over x plus x squared. This is one possible way. And for another way is to take compactly supported function. That means that, okay, maybe I'm not going to explain this one. Okay, and here in this picture, you can see the values of the graphs of the function phi, which is scaled in that way, which was presented before. So, for instance, starting from phi being Gauss-Weierstrass kernel, we can bring the graph and we obtain something like that. And now let us take the function. You can think that we have Gauss-Weierstrass kernel, and let us think about the scaling, and let us think about taking some limits, and let us think what will happen if we take the limit when the parameter t tends to 0. Okay, so let us see. In the case when the point x is 0, then you can see that here we will have just the value of phi 0 times 1 over t. So if t tends to 0, then if the value at the point 0 is non-zero, then it tends to infinity. And in the case that the x is non-zero, then here you can see that here in the argument we have larger and larger values. And because of that, and the fact that it is integrable, so for instance, you can think that we have this function. One can know that this limit will be 0. So informally, one can say that the limit when t tends to 0, phi t x is 0 when x is not 0, and it is infinite if x is 0. Okay, and now let us construct this way of approximation. Okay, so assume that we have the function f, let's say from Schwartz class. If you don't know what it is, you can think that it is nice enough function. Okay, and let us define the convolution in continuous setting. It is defined exactly the same way as in the case of Fourier series, but now we integrate over R. Okay, so we define something like this, and now the thing which we are going to study is the limit when t tends to 0 of phi t convolved with that. And now our goal will be to study what it is. And here we have the proposition in which we can find the explanation. Okay, so if the function f is continuous bounded function, then it turns out that such a limit is exactly equal to f at the point x. And how to see this? Okay, so in order to see this, let us just take this convolution of f with state phi. Okay, and then just write down the definition of this. This is just the definition. Okay, and now let us look at this integral. Okay, and now you can see that in this integral we can use some substitution, and if we use the substitution, that y1 will be t times y. Then after the substitution, we will see that this t from the substitution and 1 over t will cancel out, and here we will have y, and here instead of x minus y, we will have dy. So something which is very basic. Okay, and now let us look at the function inside the integral. Okay, so the function f is,
Sorry, shouldn't y1 should be maybe equal to y over t's, or is it right?
it depends how do you write down the substitution.
Yeah, it depends which one is the y1.
Okay, okay, so maybe I will erase this, but at this point, this is correct. Okay, and if you look at the function which is inside, then it is quite easy to find what is the pointwise limit. So the pointwise limit at the point y, here we will have nothing but that the function f is continuous, phi is also continuous, so it is nothing but fx times phi at the point y. Okay, and now the thing which one can note is that the f is bounded, phi is integrable, so using Hilbert theorem, one can say that we can pass the limit. So we do so we put the limit inside, and if we do so, we have something like that. Okay, and now inside the integral, we see that the fx is independent of y, so we can put this outside, and if we do so, we can see here fx integral of phi, but the integral of phi, it was 1. We are done. Okay, so we have something like that, and because of this result, this family of scale function phi somehow is called approximation of identity, and this is because somehow it approximates the function. It is
I think that the microphone doesn't work.
okay. Okay, I will try with this new microphones. It's somehow okay.
Okay, let's try with the.
Okay, so now can you hear me? Okay, okay, so we have something like that, and it turns out that such a function, such that if we convolve this function with any f, you will still obtain f. Such a function doesn't exist, but it turns out that somehow this family approximates such a function. Okay, and the next remark, and the remark is that I am not going to go into details, but for instance, if you assume about the function phi that it is nice enough function, so for instance, Schwartz class function, then it turns out that the convolution of f with nice function is nice function, so somehow this gives a way to approximate function which is not necessarily nice, but by smooth function. Something like that. And the next remark is that if we come back to the very beginning Fejér summation method, then one can treat that this is the special case of that thing. So one can think that our function phi can be treated as f1 and phi 1 over r. One can say that it is the next Fejér kernel. I'm not going to go into details, but interesting exercise for you, because maybe at this point it is not so obvious. And the exercise is to explain why that Dirichlet summation method doesn't fit the scope which we have here. Because we know that somehow Dirichlet summation method is not so nice. Okay, interesting question. Okay, and the next approximation result theorem, which I am going to explain in some details. Okay, so let us take the approximation of identity in the previous sense, and then we have another result, and this time it is LP result. And the result is that if we take the limit when t tends to 0 of LP norm of convolution of Ct with f minus f, then it is 0 when we have f, which is the function from LP, where p is the parameter between 1 and infinity. And a quick recall, if you don't know this, is a quick recall is that LP norm is equal to such an expression. Okay, so now let us try to understand this. I decided to give the proof of this because in this theory, sometimes I think that the proof are more important than the statements of the theorem, because sometimes it may happen that you have, for instance, different assumption on f, and you have to know how to deal with this, with your specific situation. Okay, so let us try to prove this LP result, and this will be epsilon delta proof. So let us take epsilon. Okay, and what we have to prove? We have to prove that there is delta such that if t is between 0 and delta, then our quantity, which we are going to estimate, is smaller than epsilon. Okay. So now what we have to do? So here we have this difference of these two things. So let us take that. And now for the first part, which we can see here, we can just use the definition and use the substitution which I have used previously. So here, my first term, which I have here, can be written down like that. Okay, this is just the definition. And now I am going to estimate the difference. And in order to be able to do so, I am taking my f, and in some artificial way, I can multiply this by 1. And on the other hand, 1 is equal to this integral phi. So in some artificial way, I can write down this like that. Again, nothing happened. Okay, and now the thing which you can see that here inside the integral, I have the difference of f at two various points, where usually this ty is a small one. Okay, so now for given epsilon, it turns out that there is delta such that if h is smaller than delta, then the LP norm of the difference of the function f translated in the argument by h and the function f is smaller than epsilon divided by some quantity. It is just the choice of delta. Okay, and I think that maybe the proof of this is not not so straightforward, but you can, for instance, check this on simple function, and this is the case. Okay. And now on the other way, if we have this delta fixed, then it turns out that we have the following situation for our phi. So if we have your phi like this, and then it turns out that if we integrate over a very large ball, let's say like this, then the integral outside this large ball will be small. So now I'm going to use this property. So if we have fixed delta, then one can find t, which will be such that the integral of this over the ball of center 0 and this radius will be smaller than that. Okay, and now it is time to deal with our quantity, which we are going to estimate. So I am writing down this. This is nothing by the definition. I am just taking this thing and I am just putting LP norm. And now I'm going to use something which is called Minkowski inequality to put the LP norm inside the integral. Okay, if you don't know what is Minkowski inequality, you can think that P is equal to 1, and then in that case, it is nothing but Fubinity or changing the order. Okay, so now I am going to estimate this quantity. Okay, and in order to do so, I am taking this integral and I am splitting this integral into two parts. The first part is the part which is inside the large ball, that is this one, and the part which is outside. Okay, and then for my first part, I can see that here my y is smaller than delta over t. So here I have t times y. So this thing which I have here is smaller than delta. And I know that for translation, which is smaller than delta, this quantity will be smaller than exactly this one. And then I have another part which is outside the large ball. And for this part outside the large ball, I can just estimate this LP norm by triangle inequality by the sum of 2 times LP norm of f. And then on the other hand, I know that the integral of phi outside the ball is very small in the sense which I have here. And then finally, it is quite technical thing, but I can glue together these estimates and finally I can get epsilon. And this is all. Okay, so this is the end of the proof. And in fact, this is the last proof of my talk, but maybe the interesting thing is corollary of this and the important question and how it leads to Hardy spaces. And as the consequence of this, we know that there is pointwise convergence on the subsequence. That means that we know that there exists a sequence of tk, depending, of course, on f, such that the limit when k tends to infinity of these quantities is equal to f of x almost everywhere. So this is consequence of LP convergence. Okay, but now we have more general question. Assume that the function f is in LP. What about the pointwise limit almost everywhere? Not up to subsequence, but in general. Okay, and the answer to that question is that for the function, which is LP function, this limit exists almost everywhere, but it is not so easy to prove this, not so straightforward. And moreover, it turns out that maybe we need some extra assumption on phi. Okay. So now the proposition, how to deal with this question. Okay, so I think that we can assume that we have function phi, which is nice enough function, Schwartz class function. And then the proposition is that the following set, the set of those functions from LP for which this limit existent is equal f of x almost everywhere is closed in LP. And it turns out that such a proposition is enough to claim that the limit exists almost everywhere for any LP function. Why? Because if we come back to our proposition 1, it turns out that we have proved this result for, let's say, Schwartz class function f. And this set is closed in LP. And so we have proved that we have such a convergence for nice enough function. But on the other hand, nice enough function are dense in LP. So if it is closed, it should be the whole space. Okay. And I am not going to go into details of the proof, but the standard way to prove this is, well, so we are going to prove that it is closed. So let us take the sequence of functions from the set A converging to F. And these functions are from A, and we would like to show that the limit is also in A, standard way. Okay, so in order to do so, let us fix lambda and consider the measure of the set of that points for which such a limit is greater than lambda. I am not going to give you the details, but it's a standard way to consider something like that. Okay, and now we know that our fn's are from A. So here we know that for fn, we have that the limit of this quantities is equal to that. So in artificial way, I can put fn here for any n. Okay, and then if I have the measure of the set of that points where I have this, and here I can see that this is sum of two quantities. And if it is the case that the absolute value of the sum of two quantities is greater than lambda, then the measure of the set can be estimated by the measure of the set of that points for which the sum of absolute values is larger than lambda. And if it is the case that sum of them is larger than lambda, then at least one of them should be greater than lambda half. So I can estimate this thing by the sum of two quantities. Okay, so it is quite technical, but what is important here? I will highlight this in green. The most important thing is that here you can see that we have to study something like supremum over these quantities. Supremum of over t of phi t convolved with f. And it turns out, which is crucial for us, that such a mapping, which for function f assign the supremum over all t of convolution of phi t with f is called maximal function. Of course, it is just one possible definition. The maximal function is something which is much more general, but here we have seen that it appears in quite natural way. Okay, and now for general function, maybe it is the case that it is something which is very large, but it is the case that we have the very basic maximal function theorem. So the theorem is like that. So if our exponent p is greater than 1, then it turns out that the maximal function operator is operator which is bounded on LP. which means that there is a constant C such that for any function f in LP, the LP norm of such a maximal function is estimated by C times LP norm of f. Okay, so we have such a result, and this result, I am not going to go into details of the proof, but it will be enough to prove, to come back to this proof, and if we have this, we can finish this proof.
So
But,
this operator is non-linear, yes?
Yes, but it's sublinear. Okay. Okay, so we have this result for P, which is greater than 1, but it turns out that the case of P, which is 1, it is completely different. Why? We can prove, I think it is something which you can do by yourself if you just calculate the supremum. If you want, you can do so. So the negative result is that there is function in L1 such that such a supremum is not L1 function. So it is not the case that it is bounded operator. Okay, but we have the positive result. We have something like weak type 1,1, and this weak type 1,1 is the result that there exists a constant such that for all lambda and all L1 function, we have the bound at the measure of the that points in Rn for which the supremum is greater than lambda is estimated by C times L1 norm of the function f divided by lambda. And in fact, this weak type 1,1 result is enough to deal with pointwise convergence problem. So using this, instead of boundedness result, we can come back to the proof and finish this. Okay, but now the conclusion. So we know that we have negative results, but what about the functions for which this maximal function is still in L1? So the thing which we can consider is the subspace of L1 of those functions for which the maximal function is still in L1. And for this subspace, we have the special name, and the special name is Hardy space. And it turns out that this is Banach space with the norm, which is given by the L1 norm of the maximal function.
Sorry, the very fact of the linearity of the space is related to the fact that this maximal operator is sublinear, yes? Is that right?
Uh-huh.
Okay, thank you.
Okay. Okay, so we see that this space somehow comes in natural way from study of Fourier series or pointwise convergence, very natural question. Okay, so this is Hardy space, which is defined or characterized by maximal function. Although it turns out that this space is well known in harmonic analysis, and we have several equivalent definition of the space. And now I am going to just state some of them. And in fact, looking from the historical point of view, I should start with this definition, because this is somehow the original definition of the space, but I wanted to show you the connection between the spaces and the Hardy space and the well-known question. So I decided to start with maximal function, but we can also look at the Hardy space like that. Okay, so suppose that we have the function u, which is harmonic in the upper half plane. Harmonic in the sense that it is real part of analytic function. Okay, and now we have the question what should we assume about the function u in order to guarantee the existence of the conjugate function v? You know the conjugate function from the complex variables is the function such that u plus iv is holomorphic in the upper half plane. And we have some technically looking condition. I am not going to go into details of this condition, but basically it means that we have the control of some integrals over the horizontal lines. And the answer to this question is given by Burkholder-Gandy-Silverstein theorem. And the statement is that such a special function, conjugate function exists if and only if some version of maximal function is in L1. I am not going to go into details, but this maximal function is supremum over, if you have point x here, it is supremum over all points from the cone, like that, in the complex plane. Okay. Okay. Okay, and then it turns out that under our condition, we have that the boundary value, that means the limit when y tends to 0 exists, and it gives us L1 function. And moreover, the harmonic function u can be reproduced from the function f as the convolution with the scale, as we have discussed before, Poisson kernel. Harmonic function result. And then we have another characterization of the Hardy space. So we say that the elements, that the function f is an element of real Hardy space if the function f comes from some harmonic function by taking exactly this limit. So the Hardy space is nothing but it is the space of boundary values of some nice enough harmonic function in the upper half plane. Okay, so now if we have our harmonic function u and we have conjugate function v, one can think, what about the boundary value, but not for the function u, but for the conjugate function. And it turns out that this limit also exists. And moreover, it can be expressed in a very special way using the function way, namely the some linear operator applied to the function f, and the special linear operator which takes the function and f and gives us the value of that limit is called Hilbert transform. And this is something which is well known because it is the simplest example of the singular integral in one-dimensional situation. And the Hilbert transform is nothing but it is convolution with principal value distribution, or without all the details, it is limit when epsilon tends to 0, 1 over pi, integral over the exterior of the ball of center x, fy integrated with x minus y. So you can see that this thing which we have in denominator is singular, and it's the origin of the name singular somehow. Okay, and for this Hilbert transform, we know that it is bounded on LP for p greater than 1 in the senses we had before. It is of weak type 1, in the sense which we had before. And it turns out that this operator is not bounded on L1. It is the analogous result. And again, it turns out, of course, we need the proof of this, but it turns out that the subspace of those functions for which Hilbert space is still in L1 is nothing but our old Hardy space. Okay, and maybe one more definition, which is maybe something thanks to which we can understand the space better. It is atomic decomposition definition of the Hardy space. So in order to define the Hardy space in this another way, we need the notion of the atom. So what is the atom? It is some special kind of, let's say, simple function. So the atom is the function on R associated with the ball, is the function which is supported by this ball. Okay, this is first condition. The next condition is that the infinity norm should be controlled by 1 over the measure of the ball, which is associated. And here we have the condition that the integral of this atom should be 0. Okay, so if we have our R, we have something B, so the atom is something which is supported in B with controlled growth and the integral 0. It is very important that the integral is 0. Okay, and now atomic decomposition characterization, very nice result. Okay, so we say that the function from L1 belongs to the Hardy space if it can be written down as the convergent series of atoms. That means there exist atoms and some coefficients lambda such that the series of coefficients is convergent and the function f can be written down as the series of atoms with coefficients lambda.
I have a quick question. So you said an L1 we say that an L1 function belongs to the Hardy space. So I think that this is something rather a theorem, yes? This atomic decomposition.
Yes, in fact, you can treat this like that. So you can think that we have 4 various definitions of Hardy space. And then it turns out that the very nice theorem is that all of them give us the same space.
So this is if and only, yes?
Yes.
Okay, thank you.
Okay. So sometimes if you want, you can define the atomic like that. Okay. And then the norm of the space is given by the infimum of the sum of the coefficients, where the infimum is taken over all representation. That means that the smallest possible somehow. And now, very nice exercise for you. It is, in fact, the same exercise which I gave you before. Okay, and the exercise is to use this atomic decomposition result, atomic characterization, to prove that the L1 space is not the same as the Hardy space. If you have this result, it turns out that it is very, very easy. In fact, without any computations. Okay. So now we have this. So now maybe quickly, let us go through some generalization of this. I tried to explain you this topics just in R1 case, but it turns out that the same thing can be generalized to Rn. And now maybe just to give you the flavor of this, the generalization of the Hardy space theorem goes through something which is called generalized Cauchy-Riemann equation. So that means now we have to start with something which is generalized half plane. We have to start with something which is called the vector of the function satisfying some generalized Cauchy-Riemann equation. And this time we don't have just 2 of them, but many, many of them, depending on dimension. And again, it turns out that n-dimensional Hardy space comes from taking boundary values of harmonic, of these harmonic functions. Okay, satisfying some ground condition. I'm not going to go into details. Okay, and now it turns out the other limits of other harmonic functions, the conjugate function also exists, and somehow they give us the operators in the way which I explained to you before, which are called Riesz transform. So again, the simplest example of singular integrals, but in Rn. Maybe you have seen this term. So this is the reason why I decided to put this here. And here it turns out that for them, we have also principal value definition. And if you want, we can compare this definition to the definition of Hilbert transform. And in fact, if you do so, you see that there's nothing but generalization. And again, we have the Riesz transform characterization of the Hardy space. It turns out that the n-dimensional Hardy space is nothing but it is the space of those functions from L1 for which all of the Riesz transforms are still in L1. Again, we have weak type 1,1 result. We have strong type PP or boundedness result on the P. Okay, and it turns out that the Riesz transform is quite interesting object. So for instance, I'm not going to go into details, but we have, for instance, Fourier analysis definition. Then we have the same for the Hilbert transform as well, but of course, I don't have time to go into details. And maybe the last thing for Riesz transform is that we have also operator theory definition. It turns out that the Riesz transforms are nothing but the composition of the partial derivative operator with something which is Laplace to the power minus 1/2 in the sense of operator theory. And it turns out that this definition can be treated as an inspiration for study Riesz transform in various contexts. So for instance, in the Dang context, which is in my research somehow. Okay, so here you can see possible other ways, possible direction to study this. And of course, you have something that is very classical, multidimensional theory. This is the last part of my talk. And the natural generalization of this is the generalization of this theory into something which is connected with spaces of homogeneous type. And if you like semi-group theory, I encourage you to study this theory. It turns out that there are connections. For instance, this one is the connection of this theory with semi-group operators. And we have also something which is multi-parameter generalization of this. It is exactly the thing which is the topic of my new research somehow. Okay, it is much more complicated. So maybe the last thing, so the multi-parameter theory is that, for instance, instead of study Hilbert transform, one can study two-parameter Hilbert transform, where this limit or supremum, depending on context, is taken over two parameters. And it turns out that one can ask about properties of operator or the associated Hardy space. And it turns out that in this case of many parameters, the theory is essentially different. So for instance, we have very complicated somehow definition of the atomic decomposition. I am not going to go into details, but the essential thing is that this time the atom is associated with the open set, not necessarily with the ball. So it's something which is much more complicated. Okay, and then roughly speaking, the topic of my research. So if we have something like double parameter Hilbert space, one can restrict the set of the parameters over which it is somehow taken. And if you do so, one can ask about properties of operator, boundedness, Hardy spaces, and it turns out that because of this restriction, it is something which is between pure multi-parameter theory and one-parameter theory. And I have already some results, but still there are many, many interesting questions in this topic. So now, thank you for your attention.
Thank you for a very nice talk. Any questions or comments, please?
Yes. Through the talk, we were discussing some, as it was called, nice enough functions, and we mentioned the Schwartz family. So can you tell what is this family?
Generally, in order to define this, I think that I need to introduce the multi-indices notion, and generally it is something which decay faster than any polynomial together with any partial derivatives.
Okay, thank you.
Okay, any other questions? Please. Adam, you would like to ask a question? No? Well, people on Zoom, maybe? No, okay. Can you tell, well, it seems that the Hardy spaces are very natural harmonic analysis. I mean, they appear in various contexts as you have shown us. Can you tell something about some applications outside harmonic analysis?
Okay,
PDEs?
so I think that it is relevant slide here because you see that here you have the Riesz transform, which is written like that. So in fact, it can be treated as if you, for instance, write down the PDE. It's maybe without writing down. It is the operator which somehow takes initial condition in the context of PDE and it returns the solution. So in order to study the solution, the thing which that is application of Riesz transform to the initial condition.
Okay,
So
okay.
maybe
Very
also
nice.
one comment. I don't know whether it counted as an application, but Hardy spaces are also example of the so-called reproducing kernel Hilbert spaces. And those spaces are, okay, so usually Hilbert spaces arise as spaces, typically L2, and we say functions, but in fact it's cheating. Those are not functions, but equivalence classes up to sets of measures 0. So usually, the usual situation is that the functional which sends f to the value at particular point is not well defined on the whole space. And those reproducing kernel Hilbert spaces are spaces which are purely functional spaces. So those spaces consist of pure functions. This functional does make sense, and this gives you the so-called reproducing kernel. And this theory, I don't know whether it has some application, but this is some part of functional analysis and operator theory. And these spaces are important, and Hardy spaces are one example of classes of this reproducing kernel Hilbert spaces. Other ones are the so-called Bargmann spaces and Siegel-Bargmann. And from different reasons, they are also important. For example, they have some application in physics as natural models for studying the so-called creation and annihilation operators, which have very nice presentation in terms of those spaces. So I don't know whether this somehow addresses your question, but just a comment.
Yes, it is quite different approach because here I have discussed the real Hardy spaces and these other Hardy spaces are something different, maybe more classical than this even.
Yeah, so typically they are defined on a circle on the disk. It depends how you view it.
Or Siegel domain, yes.
So these are analytic function on a disk, but the subspace of L2 on a circle. So this is somehow strange, but it is related to the fact that in complex analysis, the knowledge of behavior on the boundary gives you the whole knowledge what happens in the interior. So.
Okay, okay. Well, any other comments, questions? Okay, if not, let's thank Agnieszka again.